Hello and welcome to the Quick Solutions All India AIATS Test Series JEE Main 2020 Test 8 Physics. Let's go to question number 1. Question 1 says the moment of inertia of an equilateral triangular plate of mass m and side length L about centroidal axis perpendicular to the plane of plate is. So we have this triangular plate, in fact equilateral triangular plate of mass m and side length L, and we have to find the moment of inertia about the centroidal axis perpendicular to the plane of the plate. Well, to find the moment of inertia, we think in terms of the theories, some standard results and theories like the parallel axis theorem or the perpendicular axis theorem, whatever is applicable here. So let's look at the problem in those terms. So to find the moment of inertia about the centroidal axis, let's name some axis. Let's draw this line passing through the centroid, and let's call this as, let's say, A, B. We can keep C for the center, and let's call this point O. Now we have to find moment of inertia about the axis passing through point C and perpendicular to the plane. Well, the moment of inertia about the axis AB is IAB, and this is, if this height is h, then IAB is equal to mh square by 6, which is equal to m by 6, and h will be root 3l by 2. On simplifying, we get this as m into 3l square divided by 24, or simply ml square by 8. We have this. Now we can find moment of inertia about this axis. Let's call this C dash. So ICC dash we can find using the parallel axis theorem, because ICC dash will be, applying the parallel axis theorem, IAB minus m into d square, where d is this length, and we can see that the value of d will be h by 3. So that means this is equal to ml square by 8 minus m h by 3 whole square, that means mh square by 9, and the value of h square is 3l square by 4. So on simplification, this turns out to be equal to, we can take, here is 12, here is 8, so let's take 24 as the LCM, and so this is 3 minus 2 ml square, or this is ml square by 24. This is ICC dash. What we can do is, we can also find, let's call this point O dash, IOO dash, and then by applying the perpendicular axis theorem, we have moment of inertia about the centroidal axis perpendicular to the plane of the figure. So to find IOO dash, we can again use the result I is equal to mh square by 6. So if I take, OO dash is dividing the figure into two triangles. So for one triangle, if we can find IO dash, the other will also be the same. So that means we find moment of inertia about one of these triangles about OO dash and then double it. So the result will be IOO dash equals 2 times mass of each half is m by 2, h square by 6, h will be l by 2 into 1 by 6. Let's simplify this further. So this turns out to be equal to ml square by 24, and so moment of inertia about the desired axis, let's call it IC, will be equal to moment of inertia about CC dash plus moment of inertia about OO dash using the perpendicular axis theorem, and this is equal to ml square by 24 plus ml square by 24, which will simply be ml square by 12. If you look at the options, it is clearly matching with option 1. So option 1 is correct. Let's go to the next question now. Question 2 says a ball of mass 2 kg is projected with velocity of 20 meter per second from ground if the minimum kinetic energy of the ball during the motion is 144 joule, then the range of projectile is. Okay, so we have been given the speed of projection, the mass, and also the minimum kinetic energy of the ball during its flight. So we know that the minimum kinetic energy of the projectile will be when it is at the highest point of its trajectory, and at the highest point its velocity is simply the horizontal component of velocity. That means we have been given the expression 144 joule is nothing but half m, which is 2, into Vx square, and if we solve, Vx will be under root of 144, that means 12 meter per second. So we can take the horizontal component of velocity of the projectile as 12 meter per second, and which means the vertical component of velocity of projection, that means the vertical component of the initial velocity, uy, will be under root of v square, that means 20 square minus Vx square, and if we put the value of Vx as 12, this is 20 square minus 12 square, that means under root of 256, which is nothing but 16 meter per second. That is uy. And to find the range, we know we can write range as u square 2 sine theta cos theta, where theta is the angle of projection with horizontal, by g. In this case, u square will be 20 square, 2 is 2. Sin theta will be uy upon v, that means 16 by 20, which is simply 4 by 5. So this is 4 by 5. And similarly, cos theta will be Vx upon v, that means 12 by 20, or simply 3 by 5. The value of g we take as 10. And then let us solve now. So this turns out to be equal to, this is 400 and this is 25. We can divide 400 by 25. This is 1. 25 once is 25, and then 16 it is. So we get 2 into 4, 8. 8 into 3, 24. 24 into 16, or 24 into 1.6 rather, directly we can put it here, which is 4 here and then 38 here. So this comes out to be 38.4 meter range, which is matching with option 3. Let's go to the next question now. Question 3 says a car is moving towards a vertical wall with constant speed of 18 km per hour and blowing horn of frequency 300 Hz. The beat frequency heard by the driver is, and speed of sound is given as 330 meter per second, and then there are 4 options. Well, obviously the question is based on Doppler effect of sound, and the 2 frequencies that the driver will hear, one is the original frequency emitted by the sound because he is moving with the car, and let's find the other frequency. For the other frequency, let's call it f dash, or rather f double dash, will be equal to f naught, which is the frequency emitted by the source, and we first find expression for the frequency heard by the wall. So that will be f naught into speed of sound, let's say it is v, divided by v minus vs, because the source is approaching the wall, and this is the frequency reflected by the wall, but because the driver is himself moving, so now driver becomes the receiver, and so the frequency that he will hear is this multiplied by further v plus vs divided by v, where again, as I said, v is the speed of sound. So this is simply f naught into v plus vs divided by v minus vs. So the beat frequency heard by him will be f double dash minus f naught, and that means it is f naught, which is 300 Hz, taken as a common, and this minus 1, so it is v plus vs divided by v minus vs minus 1, or further simplifying and putting the values in the numerator, we will have the v will get cancelled, 2 times vs, so 2 times vs, and vs is 18 km per hour, which is 18 into 5 by 18, that means 5 meter per second. So we put it as 2 into 5 divided by V minus Vs is 330 minus 5, that means 325 Hertz. On simplifying, this comes to about 9.2 Hertz. So among the options, it best matches with option 2. So we take option 2 as the correct option for question 3. Let's move on to the next question now. Question 4 says, a non-conducting ring of mass m and radius r has uniformly distributed charge q and is placed on a smooth horizontal surface in a uniform cylindrical magnetic field B as shown. If the magnetic field is suddenly switched off, then angular speed of ring will be, and these are the 4 options. We have to find the angular speed of ring when magnetic field B is switched off suddenly. Well, as far as concepts are concerned, the concepts involved here are electromagnetic induction, and further in electromagnetic induction, we are concerned with the induced electric field, and further this induced electric field will apply a torque, and that torque in turn will produce an angular impulse, and that angular impulse will be finally equal to angular momentum I into omega. So let's start with the expression angular impulse J equals I omega, where I will be mr square, and of course omega is what we are supposed to find. Coming to J, J is the angular impulse that is equal to the torque into whatever small interval of time delta t for which the torque has acted and for which the magnetic field has become 0 from initial value B. The torque itself is going to be equal to electric field into Q into R, and then of course there is delta t. Now how to get electric field? We know that E into 2 pi R in this case is equal to the rate of change of flux, which is pi R square B by delta t, and that means we have E into delta t simply equal to R B by 2. So we have E delta t equals to B R by 2, and we can of course substitute it here. So that will give us I into omega, and of course we also equate J with I omega, equals Q R, and E delta t, for E delta t we put R B by 2. So this is Q B R square by 2, and I after all is mr square. So we have mr square, or rather let me put it in small case, mr square into omega equals QBR square by 2. We can strike off this r square, and so the expression for omega is simply then QB by 2m. QB by 2m. Let's look at the options. Well, it's matching with option 3. So we can take option 3 to be correct for question 4. Let's go on to the next question now. Question 5 says, a uniform rod of mass m and length L is suspended as shown in figure. A particle of equal mass m moving horizontally with velocity v0 hits the rod at lower end and sticks to it. If the rod moves up to horizontal position, then v0 is equal to, well, in terms of concepts involved, there is this collision happening, and in this particular collision the angular momentum about the hinge will be conserved, and after that whatever is the mechanical energy of the rod, that mechanical energy after the collision will be conserved. The mechanical energy before collision will obviously not be equal to mechanical energy after the collision, but once the collision has happened, subsequently its mechanical energy, the mechanical energy of the rod and the particle system is going to be conserved. So let's write the equation, the first equation for conserving angular momentum about the hinge, and that will give us the angular momentum before the collision is mv0 L. So mv0 L is the angular momentum before collision, and after collision it is I into omega, where I will be, for the rod itself it is ml square by 3, and for the particle it is ml square into omega. We can call it, or rather omega naught or omega, whatever you call it, let it be omega only. So on the right hand side, if we simplify, it is 4 by 3 ml square into omega, and on simplification we can see that the value of omega will be 3V0 upon 4L. Right? Now from this point on we simply conserve the mechanical energy, and so the initial mechanical energy of the rod and particle system is 1 by 2 I. We have already seen the value of I is 4 by 3 ml square, so 4 by 3 ml square into omega square, which is 3V0 by 4L the whole square. That means it is 9V0 square by 16L square, and this is equal to, all of this kinetic energy is converting into the gravitational potential energy, and when the rod becomes horizontal, the gravitational potential energy has increased by mgl plus mgl by 2. That means 3 by 2 mgl. Let's simplify this and find the expression for V0. So this L square cancels with this L square, and then this 3 and this 9 and this 3 will all cancel. This 2 will cancel with this 4 will cancel, and this is 4 here. You find that we get V0 is equal to simply 2 root GL, and which matches with option 3. So option 3 is correct for question 5. Let's go on to the next question now.